Imagine a predator that makes no sound. It reflects no light, emits no heat, leaves no trace. It moves through the cosmic darkness at 45 kilometers per second, faster than a bullet, though for space, this is merely a leisurely stroll. This predator weighs 7 times more than our sun, yet its size is comparable to a medium-sized city. It warps the very fabric of space around itself, creating a gravitational whirlpool from which even light cannot escape. This is not science fiction. This is the reality of our galaxy. Rogue black holes, solitary wanderers of the Milky Way, expelled from their parent star clusters billions of years ago. According to astronomers' estimates, there could be up to 100 million of them in our galaxy alone. 100 million invisible traps drifting in the darkness between stars. And one of them might be quite close, just a few thousand light years from Earth. How are these cosmic ghosts born? Where do they come from? And most importantly, how do you find something that is, by definition, invisible? The story of every rogue black hole begins with a catastrophe of cosmic proportions. 7 billion years ago, in a distant corner of the young universe, a giant star was dying. Its mass was 25 times that of the Sun, and it had lived a bright but short life, just a few million years. For comparison, our Sun has been shining for nearly 5 billion years and will live about as long again. But the more massive the star, the faster it burns through its thermonuclear fuel. When the hydrogen in the core was exhausted, the star began burning helium, then carbon, then neon, oxygen, silicon. With each new fuel, reactions proceeded faster and more violently. The star's core became a cosmic matryoshka doll, layers of different elements, one inside another, each at its own temperature, each generating the next, heavier element. Finally, iron began forming at the very center, and this became the death sentence. Iron is the limit. No energy can be extracted from it through thermonuclear fusion. The iron core grew like a malignant tumor in the star's heart until it reached critical mass, about 1.5 solar masses compressed into a sphere the size of Earth. Temperature reached 10 billion degrees. Density exceeded all conceivable limits, and then the core collapsed. The collapse occurred in a fraction of a second. Atoms were destroyed. Electrons were pressed into protons, converting into neutrons. Even quarks, fundamental particles of matter, lost their individuality. Matter compressed into a point of infinite density, creating a tear in the very fabric of reality. A black hole was born. The star's outer layers, deprived of support, fell toward the center at a quarter of light speed, then rebounded from the incredibly dense core, generating a supernova explosion. For several weeks, this dying star shone brighter than 100 billion suns, illuminating half the galaxy. But the black hole itself remained invisible, the dark heart of a blinding explosion. However, this explosion, like most supernovae, was not perfectly symmetrical. Imagine an irregularly shaped balloon bursting. Air escapes with different force in different directions. The same happened with the star. The uneven ejection of matter and asymmetric neutrino radiation gave the newborn black hole a powerful impulse, a phenomenon astrophysicists call the natal kick. Just as recoil pushes a shooter backward when firing a rifle, the asymmetric explosion hurled the black hole into cosmic space. The velocity of this kick can reach hundreds of kilometers per second. For comparison, this is hundreds of times faster than a flying bullet. If a black hole moved at such speed on Earth, it could circle the planet along the equator in 2 minutes. Recent 2024 research confirmed that black holes indeed receive such natal kicks. Studying the VFTS 243 system, a binary star system with a black hole, scientists were able to estimate the velocity at which the black hole was ejected at birth. It turned out these kicks are real, though somewhat weaker than those of neutron stars. But even a relatively small kick of 45 kilometers per second, and many receive speeds of 100-200 km/s or more, is sufficient for a black hole to break free from its parent star cluster and begin its solitary journey through the galaxy. Thus are wanderers born. Milky Way did not arise overnight. Its history is a story of countless mergers and absorptions. Billions of years ago, dozens of smaller galaxies collided, merged, were torn apart by tidal forces. Each of these ancestor galaxies had at its center a supermassive black hole, a gravitational anchor holding the stellar cluster together. When two galaxies merge, their central black holes begin a cosmic dance of death, slowly approaching until they merge into one even more massive black hole. This process can take millions of years, but not all black holes reach the finale. Computer modeling using the Romulus software suite revealed something surprising. Many black holes remain on the outskirts of galaxies, continuing to wander billions of years after the merger. According to estimates by researchers from Harvard University and Yale University, a Milky Way mass galaxy may contain an average of 12 supermassive rogue black holes, each weighing from 100,000 to 1 million solar masses. 12 supermassive wanderers, plus millions of stellar mass black holes left after supernova explosions. They all move in their orbits around the galactic center, invisible, inaudible, almost undetectable. These rogue black holes don't just drift aimlessly. They can exert gravitational influence on passing stars, changing their orbits. They can capture gas clouds that begin rotating around them, heating up and emitting X-rays. But if there's no matter around the black hole to consume, it remains absolutely dark, a ghost in the cosmic night. How do you find an object that emits no light? This is one of the greatest puzzles in modern astronomy. The answer came from Albert Einstein, though he never thought about black holes himself. In his 1915 general theory of relativity, Einstein showed that mass curves spacetime. Imagine a tightly stretched fabric with a heavy ball placed on it. The fabric sags around it. Similarly, a massive object curves space itself. Light passing near such an object follows a curved path, like a marble rolling on the sagging fabric. This effect is called gravitational lensing. Massive galaxies can create entire rings and arcs of distorted light from distant objects. But even a solitary black hole with a mass of just a few suns creates a noticeable effect. It acts like a magnifying glass, bending and amplifying the light of stars passing behind it. This phenomenon is called gravitational microlensing. Imagine a black hole moves in front of a distant star. The star suddenly becomes brighter 2, 3, even 10 times. The brightness increases smoothly, reaches a maximum, then decreases just as smoothly. The entire process can take from several days to several years, depending on the black hole's mass and its motion speed. The brightness curve has a characteristic symmetric shape, like a hill or bell. But the most interesting thing happens if you observe very carefully and for a very long time. As Earth moves in its orbit around the Sun, our viewing point changes. This is called parallax. If a microlensing event lasts long enough, months or years, parallax distorts the symmetric brightness curve, adding characteristic bumps and asymmetry. From these distortions, the mass of the invisible object can be calculated. Moreover, the black hole doesn't just amplify the star's light, it also shifts its apparent position in the sky. The Hubble Space Telescope is powerful enough to detect this tiny shift, which can last for years even after brightness returns to normal. June 2011, two automated sky surveys, OGLE, Optical Gravitational Lensing Experiment, in Poland, and MOA, Microlensing Observations in Astrophysics, in New Zealand, simultaneously detected a strange event. A star in the direction of the galactic center, about 20,000 light-years from Earth, suddenly began brightening. The event received an official designation, OGL-2000 and 11BL-462/MO-2000 and 11BL-191. But this was no ordinary brightness increase. The event lasted an incredibly long time, more than 270 days, almost 9 months. The brightness curve showed characteristic signs of parallax, and most interesting, the star's apparent position in the sky was slowly shifting. Astronomers immediately pointed the Hubble Space Telescope at the object. Week after week, month after month, year after year, the telescope collected data. Observations continued for 6 years, from 2011 to 2017. Data analysis took several more years. A team led by astronomers from the University of California, Berkeley meticulously measured the star's tiny shifts, less than 1/1,000,000th of a degree. They built models, checked alternative explanations, double-checked calculations. In 2022, the results were published. An invisible object with a mass of about 7 solar masses passed in front of the star, bending its light with its gravity. Distance to the object, only about 5,000 light-years. By cosmic standards, quite close, almost in our galactic backyard. This couldn't be a neutron star, too massive. It couldn't be an ordinary star or white dwarf. They would emit light. It couldn't be a binary system with smaller masses. The data didn't match such a model. Only one possibility remained, an isolated black hole. The first stellar mass rogue black hole had been found, and it turned out to be surprisingly close. The 2022 discovery was just the tip of the iceberg. In recent years, astronomers have discovered numerous rogue black hole candidates using a combination of ground-based surveys and space telescopes. In 2020, 13 rogue supermassive black holes were announced in dwarf galaxies. These objects weigh from 100,000 to 1,000,000 solar masses and are located not at the centers of their galaxies, but on their outskirts, a clear sign they were displaced by galactic mergers. Some actively consume gas and shine in X-rays, revealing their presence. Computer modeling paints an even more impressive picture. The Romulus simulation showed that about 10% of a galaxy's central supermassive black hole mass could be in rogue black holes. For the Milky Way, where the central black hole Sagittarius A weighs about 4 million solar masses, this means approximately 400,000 solar masses scattered as rogue black holes throughout the galaxy. How many are there really? Estimates vary, but most researchers agree on numbers ranging from tens of millions to 100 million stellar mass black holes, 5 to 100 solar masses in the Milky Way alone. This means approximately 1 black hole per 1,000 stars. Sounds frightening? Actually, we're incredibly lucky. Space is vast. This is hard to grasp intuitively, but the numbers speak for themselves. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. That's more than 40 trillion kilometers. If the Sun were the size of an orange, Proxima would be another orange somewhere 500 kilometers away. Now imagine 100 million oranges scattered across an area 100,000 light-years in diameter, roughly the diameter of the Milky Way's disk. What's the probability that one of these oranges would collide with ours? Astronomers have calculated. The probability that a rogue black hole will exert gravitational influence on the solar system in the foreseeable future is vanishingly small. According to researchers' estimates, such an event might occur no earlier than in 100 billion years. For comparison, the current universe's age is only 13.8 billion years. Moreover, even if a rogue black hole passed relatively close to the solar system, say, within a light-year, it would unlikely significantly affect Earth's orbit. Gravitational influence weakens with the square of distance, so even a 7-solar-mass black hole at 1 light-year distance creates gravitational attraction trillions of times weaker than the Sun's gravity on Earth's orbit. For a black hole to pose a real threat, it would need to pass within 1/10 of a light-year, about 6 trillion kilometers of the solar system. And even in this case, the consequences would be not catastrophic, but rather interesting. Outer planets' orbits might slightly change. Some Oort cloud objects, the distant cometary shell of the solar system, might be ejected into interstellar space or, conversely, directed toward the inner planets. But the probability of even such a relatively close passage during the solar system's lifetime, 4.6 billion years, is less than 1/10,000%. We are safe, for now. But not all objects in the universe are as fortunate as Earth. Rogue black holes do sometimes encounter stars and other objects on their path, and when this happens, the consequences can be spectacular. If a star passes close enough to a black hole, within a few radii of the black hole itself, tidal forces tear the star apart. This phenomenon is called a tidal disruption event, TDE. The star's outer layers stretch into a long spiral, spiraling around the black hole. Gas heats to millions of degrees, emitting a bright burst in X-ray and ultraviolet ranges that can be brighter than an entire galaxy. Such events are relatively rare, about 1 per 10,000 years in a typical galaxy. But considering the observable universe contains trillions of galaxies, astronomers register several dozen such events each year. Even if an encounter doesn't lead to star disruption, gravitational interaction can significantly alter its orbit, ejecting a stellar system from the galactic disk into the halo, a vast spherical region around the galaxy where star density is thousands of times lower, or conversely, slowing the star so much it begins falling toward the galactic center. Planetary systems' fate is particularly interesting. If a rogue black hole passes through a planetary system, its gravity can tear apart the family of planets. Some planets may be ejected into interstellar space, becoming rogue planets, cold, dark worlds eternally drifting between stars. According to some estimates, there may be more such orphan planets in the Milky Way than planets orbiting stars. Other planets might be captured by the black hole itself, forming an exotic system, a planet orbiting a black hole. Such systems could theoretically exist for billions of years, though the planets would be absolutely dark and cold. Black holes don't emit light like stars. The story of searching for rogue black holes is only beginning. Over the past 20 years, astronomers have learned to find them through gravitational microlensing, but most events don't last long enough for detailed study. Of thousands of registered microlensing events, only a few dozen may be black hole candidates, and only a few are confirmed with high confidence. But this is about to change. In 2027, the Nancy Grace Roman Space Telescope is scheduled for launch, the next generation after Hubble. One of its main tasks is the Galactic Bulge Time Domain Survey, a large-scale search for microlensing events. Over 5 years of operation, the Roman telescope should detect thousands of such events, including hundreds of black hole candidates. The advantage of a space telescope is that it can simultaneously measure both brightness and stellar positions with incredible accuracy. This will allow determining invisible object masses much more reliably than currently possible. While Hubble could study a few events over years of observations, Roman will find several events every month. Additionally, the ground-based LSSD, Large Synoptic Survey Telescope, currently under construction in Chile, will photograph the entire southern sky every few nights. Over 10 years of operation, it will discover millions of variable objects, including thousands of microlensing events. Although ground-based telescopes are inferior to space telescopes in position measurement accuracy, their enormous field of view compensates for this disadvantage with quantity. The most interesting developments will occur when data from different instruments are combined. An event discovered by LSSD can be studied in detail by the Roman telescope, then analyzed by radio telescopes and X-ray observatories. Such a multi-wavelength approach will not only find black holes, but also study their properties: mass, velocity, direction of motion. Over the next 2 decades, we will compile the first complete map of the rogue black hole population in the Milky Way. This will open a new chapter in understanding galactic evolution and the fate of massive stars. But microlensing isn't the only way to find rogue black holes. In recent years, a completely new tool has emerged: gravitational wave detectors. When 2 black holes approach and merge, they create ripples in the very fabric of spacetime, gravitational waves. These waves propagate at the speed of light in all directions, stretching and compressing space in their path. The effect is incredibly weak. Even the catastrophic merger of 2 black holes, each 30 solar masses, stretches a kilometer of space by only 1/1000th of an atomic nucleus diameter. Yet, since 2015, the LIGO and Virgo detectors have registered over 100 black hole mergers. Analysis of these events showed that many black holes in binary systems have wrong orbits. They're not aligned with each other, as would be expected if both black holes formed from a binary star system. The explanation is simple. These black holes received natal kicks at birth. Supernova explosions pushed them in different directions, warping their orbits. This is direct confirmation that natal kicks are real and play an important role in black hole evolution. Moreover, studying merger parameters allows estimating the natal kick velocity distribution. A 2023 study showed that black holes can receive velocities up to 10% of light speed. That's more than 30,000 kilometers per second. Such a black hole could escape not just from a star cluster, but from the galaxy itself, becoming an intergalactic wanderer. Despite all achievements in recent years, we still know very little about rogue black holes. Many questions remain unanswered. How many are there really? Estimates vary from tens of millions to several hundred million in the Milky Way alone. A tenfold spread is colossal uncertainty. More accurate estimation will require detecting thousands of microlensing events and accounting for all possible observational biases. How are their masses distributed? Most discovered candidates have masses from 5 to 15 solar masses, but this may be an observational selection effect. More massive black holes create more noticeable microlensing events. Do intermediate mass black holes exist, hundreds or thousands of solar masses wandering the galaxy? Theory predicts their existence, but observations haven't confirmed it yet. Where are they going? Each rogue black hole follows its own orbit around the galactic center, but their velocities and directions are highly diverse. Some move slowly, remaining in the galactic disk. Others received such powerful natal kicks they soared into the halo or even left the galaxy forever. Mapping their movements will give us unique information about galactic dynamics and dark matter distribution. Can they have companions? Theoretically, a black hole formed in a binary star system might retain its companion star even after receiving a natal kick. Such exotic systems, a star orbiting an invisible black hole, racing through the galaxy, should exist, but they're difficult to detect. The companion star would be the only visible sign of the black hole's presence. What happens at the event horizon? This is the most fundamental and perhaps unattainable question. The event horizon is the boundary beyond which the black hole's gravity is so strong that even light cannot escape. What happens to matter crossing this boundary? How does time behave near the singularity? These questions lie at the frontier of modern physics, where general relativity meets quantum mechanics, and neither theory can yet provide a complete answer. Rogue black holes aren't just exotic objects to study. They are cosmic archaeologists carrying information about the galaxy's past. Each black hole preserves memory of the star that spawned it. Its mass speaks of the parent star's mass. Its velocity and direction of motion contain information about the supernova explosion that occurred millions or billions of years ago. Its orbit reflects the galaxy's gravitational history, all mergers, collisions, and perturbations that occurred during its existence. By studying the rogue black hole population, astronomers can reconstruct the star formation history in the Milky Way. When were the most massive stars forming? How did the star formation rate change over time? How many small galaxies were absorbed by the Milky Way throughout its history? Moreover, black holes may help solve one of modern cosmology's greatest mysteries, the nature of dark matter. About 85% of all matter in the universe exists as dark matter, invisible substance that manifests only through gravitational influence. Some theories suggest that part of dark matter might consist of primordial black holes, objects formed not from stars, but directly from density fluctuations in the early universe, within a fraction of a second after the Big Bang. Accurate counting of stellar origin rogue black holes will allow constraining the possible fraction of primordial black holes in dark matter composition. If we find more black holes than can be explained by stellar evolution, it would be a sensational discovery, direct proof of primordial black holes' existence. Let's imagine for a moment an incredible scenario. What would happen if a rogue black hole actually passed close to the solar system? Not within 1 light-year, where its influence would be negligible, but much closer, say, at Neptune's orbit distance, approximately 30 astronomical units from the Sun. 1 AU is Earth's distance from the Sun. First, astronomers would notice strange perturbations in trans-Neptunian objects' orbits, icy dwarf planets and comets beyond Neptune's orbit. Their motion would become chaotic, unpredictable. Then the outer planets' orbits themselves would begin slowly changing. Neptune, Uranus, possibly Saturn, all would feel the invisible visitor's gravitational pull. A 7 solar mass black hole passing at 30 AU would create gravitational attraction about 1,000 times weaker than the Sun's pull on Earth's orbit. Sounds minor, but for outer planets, this would be a colossal perturbation. Over several months of the black hole passing through the solar system's outer part, gas giant orbits would shift by millions of kilometers. More dramatic consequences would affect the Oort cloud, a huge spherical shell of trillions of icy objects surrounding the solar system at distances from several thousand to 100,000 AU. The black hole's gravity would eject millions of comets into the inner solar system. Several years after the black hole's passage, Earth's sky would light up with hundreds of bright comets, and the risk of collision with a large object would increase thousandfold over several centuries. But the most eerie thing, we wouldn't see the black hole itself. Even at Neptune's orbit distance, a 7 solar mass black hole would appear as an absolutely black disk only about 40 kilometers in diameter. Against the starry sky background, it would be practically invisible, revealing itself only through distortion of distant stars' light, gravitational lensing effect. Astronomers could detect it only through its gravitational influence on planets and solar system small bodies. This would be a race against time. Calculate the invisible object's trajectory, estimate its mass, understand how close it will approach, and have time to prepare for possible consequences. Fortunately, the probability of such an event is so small that there's no need to worry. But the very possibility makes us think about the fragility of our cosmic home and the invisible forces that shape the fate of planets and stars. Rogue black holes exist not only in our galaxy. They must be widespread throughout the universe, in every galaxy containing billions of stars. In other galaxies, astronomers have already discovered indirect signs of their presence. Chandra telescope observations in X-ray range revealed multiple point sources of radiation in large galaxy halos, far from star clusters where black hole formation could be expected. Some of these sources may be rogue black holes actively consuming gas and emitting X-rays. Dwarf galaxies are especially interesting, small stellar systems with masses of millions or billions of solar masses. Such galaxies are easily destroyed by tidal forces of larger neighbors. When this happens, stars scatter, but black holes, being more massive and compact, can continue moving as a group, forming dark clusters. Such clusters of invisible black holes drifting in intergalactic space could explain some anomalies in dark matter distribution observed in galaxy clusters. On universe scales, rogue black holes play an important role in mixing matter and energy. When they pass through gas clouds, their gravity compresses the gas, sometimes triggering star formation. When they merge with each other, they emit gravitational waves, carrying energy from the galaxy in the form of spacetime perturbations. Moreover, rogue black holes may be seeds for supermassive black hole growth in galactic centers. A small black hole drifting toward the galactic center can capture gas and merge with other black holes, gradually growing to millions or billions of solar masses. This process takes billions of years, but on cosmic time scales, it's quite a feasible scenario. There's something deeply philosophical in the very existence of rogue black holes. They challenge our understanding of reality and remind us of human perception's boundaries. We're accustomed to trusting our eyes, We see stars, planets, nebulae, and consider them real. But black holes don't emit light. They're absolutely black, invisible, intangible. Yet they're real, perhaps even more real than many visible objects. Their gravity warps space, changes planetary orbits, influences entire stellar systems' fate. Rogue black holes exist in a state of cosmic solitude. They have no companion star, no accretion disk of gas, nothing that would betray their presence. They move through the galaxy in absolute silence and darkness, invisible ghosts of dead stars. This suggests a thought. How many more invisible phenomena exist in the universe? How many processes, objects, even entire forms of existence remain hidden from our instruments? Dark matter, dark energy, perhaps entire dimensions of reality about which we have not the slightest idea. The search for rogue black holes isn't just an astronomical task. It's a lesson in humility and a reminder that the universe is far more complex and mysterious than it appears at first glance. It's an invitation to develop new observation methods, new theories, new ways of thinking. And it's hope. Hope that even the most invisible and elusive can be found, understood, and incorporated into our worldview. If we could detect black holes, objects that are by definition invisible, what else can we discover? Right now, at this very moment, millions of rogue black holes are moving through the Milky Way. One of them may be within a few light years of the solar system, too far to pose a threat, but close enough to be a neighbor by cosmic standards. It was born billions of years ago in a supernova explosion, received a natal kick, and embarked on its infinite journey. Over millions of orbits around the galactic center, it passed through molecular clouds, past star clusters, through spiral arms and interstellar space voids. Perhaps it passed near other planetary systems, changing their orbits, ejecting comets, creating chaos. It will never stop. Black holes have no friction, no environmental resistance. It will continue its path for billions of years until one of three things happens. It will merge with another black hole in a catastrophic explosion of gravitational waves. It will be captured by the central supermassive black hole's gravity and absorbed. Or it will drift in darkness until the very end of time, until through unimaginable eons, 10 to the power of 100 years or more, it evaporates through Hawking radiation, turning into a cloud of subatomic particles. But that won't be soon, very not soon. Meanwhile, silent wanderers continue their endless dance in darkness, invisible, inaudible, unstoppable living monuments to dead stars, ghosts of the cosmic past, travelers of eternity. And somewhere in this abyss, on a small blue planet near an unremarkable yellow star, astronomers point their telescopes at the night sky, search for tiny shifts in distant stars' light, and slowly, patiently compile a map of the invisible.